Okay, so good morning, everyone. So I'm going to continue this discussion about the problem of elimination of the unstable locus for differential operators. So I recall to you very briefly, I have this problem of to consider a differential operator that I note by phi, and the germ of this operator on a point will be called strongly unstable if these two conditions here are satisfied, right? So it should preserve the filtration given by the powers of the maximal ideal, and then it should be satisfied this property of being unstable in the preceding sense, which means that there is some coordinate system where you can exclude the origin from the Newton polyhedron, right? So I just recall this example to show to you that this. So the first condition which appears here is always satisfied when phi is of order 0 or 1. I mean, for vector fields or for function germs, but it can be even if the operator is unstable, this condition cannot hold in some case. Okay, so this here I show you an example. I was a little bit quick, perhaps like last time. So in this case, you can see that in this coordinate system, the polyhedron is separated by let's say by a plane through this point, like a plane is separated from the origin. But so the second condition here is satisfied, but the first one is not satisfied. Why? Because, well, this it's a way to see it when you, let's say, when you take the second power of the maximal idea is not sent into itself by phi, okay? Because, well, you just look at the equation here, and you see that, let's say, x squared is sent to a unit. No, sorry, x squared is sent to x. It's sent to y, in fact. Okay, so x squared is sent to y, so it maps. In fact, it maps m squared to m. Right? So this also explains to you why I need this condition for all powers k, because in fact, if you just look for the first power, you have a phi of m mapped to m, but this is not holds for the second power. Okay, so why we have to make this, let's say, stronger definition? Because in fact, I'm not able to prove that the stable locus, I mean the unstable locus, the one which I don't use the first condition, I cannot prove that it's closed. Okay, perhaps it's true, but I don't have a counterexample, but I don't know how to prove it. But this strong unstable locus is closed. Okay, so it coincides with the previous, the weaker notion when the order is more than 1, and it's closed. Well, I have written the proof here, but I think I'm not going to show you because I want to tell you about other things. And in fact, the most important part of this proof is to use these techniques from geometric invariant theory. So I'm going to give you a very brief review of these concepts of geometric invariant theory, because in fact, all the procedures that I'm trying to apply here are based on this sort of ideas, this circle of ideas. So the setup is the following. You have what we call a reductive group acting linearly on a finite dimensional vector space. Okay. So so the first thing that you want to understand, of course, is the quotient by this action. And for this, it's necessary to describe this ring of invariants. So I mean that all polynomials which are invariant by the G action, where of course the G, since it acts on the group on the space V, it acts also by on the set of polynomials by the usual let's say dual laws. Okay, so this is a very important theorem. So Hilbert's proof that proven for, let's say, for some particular case, but then has it been extended for the whole set of reductive groups, that this ring of invariants is finitely generated. Okay, so it means in fact that you can define some sort a quotient, a space which would be the quotient of V by the action of G. Okay? So there are some polynomials A1, AM, which can be chosen to be homogeneous, which generate this ring of invariants. And here we are going to be interested, in fact, in what we call the null cone. What's the null cone? In fact, is the fiber above 0 of this quotient map. Or we can also define it as the zero set of the collection of all the generators of the invariant ring. Okay. So one of the results is that each one of the level sets A1 to AN equals to constant contains a unique closed orbit. And in fact, the unique closed orbit inside the null cone is the origin. All the other orbits will contain, which are on the null cone. So there are several other orbits. We're going to see here. They contain the origin on their closure. So one of the important facts is we'd like to characterize this null cone without computing the ring of invariants, which can be quite tricky in some examples. And well, this is a very nice idea. So how can we do to compute this null cone? In some sense, you fix a maximal torus. So again, here's so now we are in a finite dimensional set. So we have this group G, and then we have some a torus inside, a copy of C to the power C star to the power n. And now you define let's say the graduated decomposition of V in this direct sum, where each alpha is let's say a generalized eigenspace associated to T. Okay. So for instance, if you take G equals to the linear group, the full linear group, this maximal torus is simply given by, let's say, a copy of in a convenient basis, a copy of the subgroup of diagonal matrices in Cn. Okay. So as in the case of in a finite dimensional set, we can define the support of a vector on the vector space V, small v, simply by taking its decomposition with respect to this direct sum, and taking the support as being all V alphas, all alpha such that V alpha is non-zero. So the components which are non-zero in this direct sum in two eigenspaces. Okay. So this is the central piece for us is the Hyrulemova Criteria, which establishes an equivalence between three conditions. So V lies on the maximal on the null cone. So it contains 0 on its closure by the action of G. If and only if there exists a maximal torus T, such that the convex envelope of the support of V with respect to this torus does not contain 0. So okay, this recalls a lot the condition of instability that I've defined in the infinite dimensional set. And there's a third condition, which is I've already also discussed it in the case in our infinite dimensional case, is that you can find a one parameter subgroup G, lambda, such that the support of V with respect to lambda has all positive, let's say, has only positive terms on its graduation. Okay. So these three conditions are equivalent. This is the so-called Hyrulemova Criteria. So for us, in fact, what we would like to do is to, well, I have defined the instability. In fact, having this result in mind, I have defined the instability by these two conditions here, right? But the Hyrulemova Criteria says that it's also defined by this first condition here, which is purely algebraic. Okay. So the first equivalence here allows, in some sense, to eliminate this existential quantifier, which appears here, right? And says that, well, in fact, to find, let's say, to prove the existence of a maximal torus, it suffices to see that V lies on the vanishing locus of the generators of the invariant ring. Okay, so in some sense, it translates this instability condition by an algebraic condition. Okay. So in fact, this is in the heart of the proof that this strongly unstable locus is closed, as I mentioned in the theorem that I have not put. Okay, so geometrically, it means the following. So V is on the null cone. It's the same thing as saying that 0 lies on the closure of orbit of G of V with respect to G. Okay, and now with this condition, with this equivalence by the Hyrulemova criteria, it says the following thing: if you can send, let's say, if 0 lies on the closure of orbit of V by G, then there is a one-parameter group lambda which also sends V to 0 on its closure. Okay. So it says that what I mean, it's this. So 0 belongs to the closure of a G orbit, the G orbit of V. If and only if we can steer V to 0 by a one-parameter group. So it's like a curve starting from V, which accumulates on 0 by along this parameter, this one-parameter group here. Okay, so this is an if and only if. So let's give some examples very quickly. So here, two classical examples. Okay, so we consider, so this is one example of examples which motivated Hilbert effect. So we consider the case of the reductive group SL2 of C. So it acts on the, let's say, on C2, and then it acts also on the space of homogeneous degree D polynomials, simply by the formula that, simply by this formula which changes the linear the coordinates x and y, okay, according to the matrix G, right? So now we'd like to understand the orbit of a polynomial of degree D by this action here. Okay, so now we use the Hyrulemova criteria to show which is the null cone. I mean, which are the polynomials whose orbit contains 0 in its closure, right? So you take this maximal torus. So the standard maximal torus on SL2 of C is this one. It's given by the, so this is a matrix with determinant 1, right? And it's diagonal 1. So it's there is in fact one. This is the so-called standard maximal torus. But of course, if you conjugate this lambda of t by any element of SL2, you obtain another torus. Okay, so we have to take into account this whole bunch of maximal torus. So you take this maximal torus, this one, which is one dimension, of course, and how it acts on a monomial. So you say you have x to the k y to the power l, and this transformation maps this to t to the power k minus l x k y l, right? It's very simple. So so how such a monomial is positively graduated? It's positively graduated when k minus l is positive, strictly. Okay. So so this means that the support of p with respect to lambda is positively graduated. Is in this let's say all its terms are positive graduated if and only if p is divisible either by x to the power d, let's say integral part of d over 2 plus 1, or of course you can, have this torus, but you can also change t to the power minus 1, and then you have the condition, this condition here. Okay. So in terms of the, let's say, if you draw the polygon of p with respect to this coordinates, you have these two configurations. You see that either all terms, all monomials should lie above the diagonal or below the diagonal. Okay, see that these are the two situations which are give a positive graduation with respect to this maximal torus, or to the inverse of this maximal torus. Okay, so by Hyrulemova criteria, the null cone is the set of polynomials. So now you have to change, of course, you have to take all possible maximal tori by conjugating this lambda by the action of SL2. And then what happens is that these terms x, let's say this factor x, becomes just a linear factor, right? So the characterization is the following. So P is in the null cone if and only if it has a root of multiplicity at least d over 2 plus 1. Okay, so it means that in some good coordinate system, you can push all the support above the diagonal or below the diagonal. Okay. Another case which we have already found is this case here. You take the x of GL2 of GL in of n of C on the matrices. Okay, so it's well known that the ring of invariants in this case are the coefficients of the characteristic polynomial. Okay, so this is the action on a matrix by conjugation, of course. And so A lies in the null cone if and only if it's nilpotent. Okay. Well, I have given a proof here, but it's very easy to show this by the Hilbert-Manford criteria. Just prove that. Well, in fact, it's a very easy way to do so. Is to put. So you put A, supposing that it's nilpotent, you put A in its Jordan normal form. And then you see very easily that by conjugating A by a matrix, a diagonal matrix, where you put some powers of T, some, let's say, nice convenient powers of T on the diagonal, you have a one parameter group which makes all coefficients of this new matrix tends to 0 as T goes to 0. Okay? So we have this condition here. A is on the null cone if and only if it's nilpotent. And in fact, this is one of the, if you recall, this is precisely one of the ways that we use it to characterize the nilpotent singularities in the case of vector fields. Okay. As you recall, we have this property of separating the support from the origin by a hyperplane. Well, so let's go back to our original problem. Okay, so I'm not going to prove, but we can use the circle of ideas to prove that the unstable locus is closed. I'm just going to show the drawing. In fact, what happens is that you just look at the initial part of the support. Okay, sorry, go just to make a drawing here. And then there is a reductive group which acts here. And assuming that it's unstable, you can make this group G separate the support from 0, but this inside the, let's say, the plane given by the hyperplane through the origin on the let's say on the space of a Newton polyhedra, and then you can use this argument of that I call the hinge argument to show that you can extend this red line to a hyperplane separating the support from it. I haven't written the details here, but I'm not going to discuss too much because I'd like to show you. So how's the problem? Now you have this locus, which is a closed analytic subset of the element space, and I'm going to formulate the problem is given a differential operator. We'd like to prove that there is a locally finite sequence of blowups. Let's say the usual problem, which will eliminate the strongly unstable locus. Okay, so the idea is that at the end we have we finish with a pair m prime phi prime where this unstable locus of phi prime is empty. Okay. So here, let's say for the moment, I'm not requiring to have a logarithmic resolution in the sense that I not included in this data the exceptional divisor, because well, for the moment, you have to see the algorithm that I'm going to propose, in fact, it does not guarantee that the centers of blow up will have normal crossings with the divisor at each step. This is something that perhaps can be incorporated in the algorithm by, let's say, by changing a little bit the invariant that I'm going to propose. But for the moment, I'm not requiring this. Okay. So what's the basic idea? It's based on the, in fact, on a thing that's called the question of Manford-Titz. So recall, I have this. I'm going to state the result. Let's say the problem in the context of finite dimensional vector spaces. So I have this reductive group, which acts on a vector space V, as we have mentioned before. And now I have a vector V, which lies on the null cone. right? So just as in the same context as before. And recall that I said that this is equivalent by the Hilbert-Manford criteria to the fact that there exists a one-parameter group lambda. Oops, no, okay. So there is a one-parameter group lambda such that you have this sort of asymptotic equation which says that lambda of t applied to v is something of the order of t to the power k times v, where k is strictly let's say greater or equal than 1. So by this I mean that when t goes to 0, lambda t of v goes to 0, right? So you can say that this k here measures somehow the order, the speed with which the vector v goes to 0 by the action of lambda. And let's note this by mu of v lambda, right? So this the greatest exponent k that I'm able to put here. Okay. So the question of Hilbert-Manford is the following: can we characterize the subset of one-parameter groups for which this order is maximal, right? So now I know that I can send v to 0 by this one-parameter groups, but I would like to know for which one of them I can send v to 0 in the fastest way. Okay, so of course I have to make this question to have a sense. You have to normalize in some way the lambdas which appear here, because if you take one of this lambda here and then you define a new one-parameter group where you change t to the power r, just like made here, okay, then of course the k, let's say the mu which appears for this new one-parameter group lambda 1 will be equal to the previous one times r. So of course you can increase this sort of order just by this sort of artificial manipulation, right? So you have to normalize in some way to look at the problem without a modulo such kind of transformation, right? So this is the content of, Kempf has answered this question in this very nice paper. It's very well written and easily understandable, even for people like me, which are not specialists on the subject. So I recommend this paper. And in this paper, he introduces a notion of a length. Okay, so a length, it's a way to measure the size of elements in the set of one-parameter groups. So I recall to you that so gamma of G is the set of all one-parameter subgroups of this group G. And now I'm going to associate a length to each one of these one-parameter subgroups. So this, but it's a let's say a real valued function like this, satisfies these two requirements. So it should be G invariant. I mean that if you take lambda and you produce another one-parameter group by conjugation, by G, sorry, the length should be preserved. Okay. And the second one is very important, is that this length should be given by inner product. So in fact, it's if you restrict this length to a maximal torus, so a maximal torus it contains a lot of one-parameter groups. So for each maximal torus of G, T contained on G, the restriction of the length to each element of T should be given by this formula here, okay, where let's say this bracket here is an integral valued bilinear form on the set of one-parameter subgroups of T. Okay, so it's let's say so in some sense we can say that this length should be sort of given by a Hilbert in a pre-Hilbert structure. Okay. This is important because we are going to use very strongly the convexity properties of this inner product. The strict convexity. Okay, so yeah, I'm going to in some sense, if you recall that I've mentioned to you this this so-called while group, which is the group which acts on the one parameter subgroups of gamma. So in fact, if this group, while the while group is sufficiently large, as in the case of where, for example, if you take G equals to the full linear group, then in fact, this group, the while group, it acts by permutation on the coordinates. And this, the G invariance of the length, essentially says that the inner product should be unique up to a constant factor. Okay, so this is very nice. It means that, in fact, if the while group is sufficiently rich, the G invariance implies that this inner product is essentially unique up to a constant factor, because you have to permute all the if you have a basis, then this while group, it can permute all elements on the basis. So essentially, it gives you the same length for all elements in a basis, and so it's unique up to a constant factor. Okay, so now using this basis, we can define finally what's the problem. So recall that I said that you have to normalize some way to make the question of this question of Mumford and Tits to make a sense. You have to normalize, and the way to normalize that is proposed by Kempf is just by defining this speed. So suppose that V is an unstable vector. So for each non-zero one parameter, so each one parameter group lambda, I will define the speed of V with respect to lambda as the quotient of the exponent k. Recall that there is this exponent k which appears, which measures the speed, let's say the order of convergence to zero of lambda t applied to V. But now I divide out by the length of lambda. So now, so you have this formal object, let's say this precise object, and I'm going to define the speed of V as the supremum of the speed of V with respect to lambda with respect to all lambda on the one parameter, on the set of one parameter. Will allow us to measure somehow how much V is unstable. Okay, so I said how fast can I send it to zero by action of one parameter groups? And now I define this optimal set, key of V, as a set of all parameter groups which realize the maximal speed. Okay, so of course it's a theorem to prove that this speed. So this is the content of Kempf's result. So we would like to characterize this optimal set, a set of one parameter groups which realizes this supremum. Okay, so this precise, yeah, I'm going to skip this, I think. Yeah, so there is how to see this speed in a geometric way. Okay, so in fact, there is a dual pair, let's say a pairing between the one parameter groups on one side and the character set and the group of characters in a maximal torus. And in fact, using this duality between the one parameter groups and the characters, you can transpose the length to a length on the set of characters. Okay, so you can, in fact, so I'm going to make the drawing to see how can we see the speed through the Newton polyhedron. Okay, so in fact, this is just a drawing. So you draw the Newton polyhedron of V with respect to a maximal torus, and then you give, let's say, one parameter group which lies on this maximal torus, let's say lambda. Okay, and well, so there is, as I say, there is a dual. By using the inner product, you can define the dual character. Okay, so this define this hyperplane here, and in fact, the speed is nothing else than this distance here, conveniently normalized. So in some way, is to measure the speed of V with respect to lambda, measures the first point of the Newton polyhedron, which touches this this hyperplane defined by lambda let's say, in a product with k equals to constant. So once you have this speed, of course, for a fixed maximal torus, sorry, yes, yeah, the speed now in absolute terms is defined by the nearest point. Okay, so now you look inside the Newton polyhedron, the point which is nearer the origin with respect to this distance function. So in this case, okay, we have this set of, let's say, of spheres. And then you see the first time that one of these spheres touches the Newton polyhedron. And as I said, by the strict convexity of the function which defines the inner product, there is this holds in a unique point. Okay, and this point is the point which realizes the maximal speed inside this torus, right? But the problem is that now you have a torus, you have a lambda inside the torus, and this realizes the maximal speed inside T. But now there is the group G, which acts, let's say, on V, but you can think as this as the group G acting, in fact, on the points of the support, right? So each time you make G acts on V, you change the support. So the question is the following. Now, when you make this whole support change, of course, you can put the point lambda farther and farther. Okay, so the question now is, how is it possible to find for which, let's say, in my notation here, for which G we can realize a polyhedron such that the nearest point is as far as possible. So it's a sort of min-max problem, right? So you minimize let's say, yes, you take the nearest point, but then you want to maximize the distance of the nearest point. So the theorem of Kempf says the following. So first of all, that there exists the set of optimal speed. Let's say the optimal one-parameter groups exist. So it means precisely this, that this speed, the supremum is sustained. And more important for us is the second conclusion. So this set exists, but in fact, you can fully characterize the set of one-parameter groups which realize this optimal speed, which is given as follows. You pick one of the elements, let's say lambda, and then you can obtain all other elements by the action of what we call a parabolic group. Okay, so what it means is you have this lambda, and then you conjugate lambda by all elements G on the group, capital G, but which are positively graduated with respect to lambda. So this is what we call a parabolic subgroup of G with respect to lambda. Okay. Okay, so this is a little bit technical, but for us the important conclusion of this is that all elements of this optimal set define exactly the same filtration of V. Okay, so we recall that was in some sense where we had to have somehow an intrinsic filtration. This is our goal, and this is precisely the conclusion. One of the consequences of this the theorem of Kempf is that in this finite dimensional setting, we precisely obtain this intrinsic filtration, which is something which is attached to V only, right? So to V and the action of the group G. Okay. So now, okay, we'd like to adapt this context, this to the context of differential operators. Of course, the basic idea is quite simple. You have this differential operator phi on a manifold, and we'd like to define some sort of speed, which will be the maximal invariant. Sorry, the main invariant will be the speed. So the measure, we would like to measure the distance between the polyhedron of phi and the origin with respect to, let's say, to a conveniently defined length. And then the local strategy, of course, will consist in blowing up with the filtration defined by the optimal one-parameter groups. Okay, so I said that this filtration is intrinsically attached to this optimal set. So why this should work? Well, if you look at the combinatorial effect of a blowing up, it's of a weighted blowing up on the nearest point, it's quite easy to see that, let's say, things should work well modulo some complicated things which can happen, of course. But okay, so let's see this drawing. So you see, now I'm drawing the neutron polyhedron of an arbitrary differential operator, right? So you don't mind what happens here in the negative part, but there is always a nearest point which lies inside the positive quadrant, right? So this is the nearest point, this black colored point here. And now when I blow up, you see that with the weight defined by this dashed arrow here, right? So you see that the effect of the blowing up, again, is to project everything on one of the coordinate hyperplanes. And of course, you see that there is a point, let's say the dashed point gets projected on the hyperplane. And of course, the resulting distance would be smaller than the previous one, right? So in some sense, if you define now the speed for the transformed object here, since there is a point which is already nearer the origin than in the previous situation, the invariant should decrease. Okay, but this, of course, is modulo this complicated phenomenon, which is the so-called compensation phenomena. So when now you take this combinatorial transformation and then you apply the translations, then of course you can have this compensation phenomena, which makes this vertex disappear altogether, and then you should, in fact, you can produce very easily examples where you should have a new polyhedron which will be far away from the origin than the previous one. So how to prevent this bad compensation phenomenon which appears by the translations? Okay. So we'd like to define in this, let's say in this context, what would be the analog of this stabilization procedure. We recall that this stabilization procedure was a procedure to prevent precisely this compensation phenomenon that we're trying to prevent here. Okay. So this is a very nice result of Kirwan and S simultaneously independent, I think. So they proved the following thing: that there is a way to characterize an unstable vector, which is, let's say, going back to the context of finite dimensional vector spaces, which is very nice and in some sense constructive, and allows us not only to define the optimal set in a sort of let's say iterative way, but also to define a full stratification of the null cone into constant speed subsets. Okay, so that is the following. So it's given by an equivalence. Sorry. So it says that you take a vector v which is unstable. Then, like you recall that we would like to look at this one-parameter groups which are optimal, right? So it lies, lambda lies in the optimal set if and only if the component of V, the smallest non-zero component of V with respect to the graduation defined by lambda, is semi-stable now with respect to the action of what they call the slice group, is the zero degree gradated subgroup of G. Okay. So, well, I'm going to try to explain this by a drawing. So you see here, there is the nearest point, right? So, and now there is I'm going to forget everything except this initial part of the polyhedron. So the supporting hyperplane which contains the nearest point, right? And now I'm going to consider only the action of the group which, let's say, slide monomials along this blue line. So this is the slice group, which is precisely the group of degree 0, the subgroup of degree 0 elements of G with respect to T. Okay. Then the idea is that this situation is, let's say, the lambda which appears here is optimal if and only if I cannot, by the only action of G, sorry, only the action of the slice group GR0 of 0, I should not be able to remove the point, let's say the nearest point from the support of the polyhedron inside the hyperset. Okay, so here I've drawn the let's say a two-dimensional picture of the face. So this is the blue face, and in order to have an optimal group, we should have the situation where I'm not able to separate inside the face let's say the blue point from the support. Okay, so in some sense, what I want to prevent is some sort of instability inside the face. Okay, so if you're not able to produce instability inside the face, it means that the group, the one parameter group, is optimal. Okay, so this precisely, you recall that this is a sort of analog of this unstabilization, sorry, of this stabilization problem that I've described to you, let's say in a more simple context. But here, what we want to do is to prevent the fact of removing the nearest point from the support inside the face by the action of the group acting just on the face. Okay. Well, why this is nice? Because, well, in the case, let's say in the usual case of reductive groups, you can prove that this slice group is also reductive. Okay, modulo, let's say modulo some the action of lambda itself, but it's essentially reductive. So in fact, when you restrict yourself to the slice, you have again a sort of geometric invariant theorem which can be applied, but now to the action of the slice group on the, let's say, the vector space defined by the restriction to this slice. So in some sense, I have an inductive procedure, which interests us too, is a problem in dimension n-1. Okay? So this in fact allows them to define what we call the Hessenling stratification, which in fact can let's say it's a very nice, well-behaved stratification of the null cone in a union of smooth algebraic sets, each one essentially given by the speed of the corresponding element. Okay, so we'd like to translate all these things to our setting. In fact, for us, the advantage is that we have this. In our case, we have this infinite dimensional problem because the group which we're trying to make act is the group of all automorphism of the, let's say, of the local ring. So it's a group of all possible chains of coordinates. It's a huge group. It's not finite dimensional. But with this strategy, in fact, to characterize the instability, we just essentially have to look at the action of these slice groups here, okay, which most of the time are going to be finite dimensional groups, which are some sort, let's say, almost nice to work with. So now, in the general context, I have 5 minutes, I think. Huh? Yeah. Okay, so I think I'm going to. So now, in the context that in our infinite dimensional context, recall that I have this one parameter groups, but now they lie inside the set of, let's say, this huge infinite dimensional group. But I can define exactly as in the case of Ness and Kirwan, I can define the lambda slice group like this. So G of lambda is the set of elements of automorphisms which are of degree 0 with respect to lambda. Okay, so let me just give you. So this is degree 0 component of the graduation defined by lambda. So let me just give you an example of this. So for instance, if you take the simplest possible one-parameter group. Yeah. So the group, let's say for a fixed system of coordinates, which acts on its coordinate by multiplying it by t. Okay. So this is the one-parameter group, which simply yes, whose graduation is just the usual homogeneous graduation, right? So it gives weight 1 to each variable, and then gives weight d to each monomial whose exponent has some d. Okay, so in this case, it's easy to see that the slice group is essentially, okay, modulo this quotient is essentially the group of automorphisms of the projective space, the usual projective space. Okay, so this is PL cell N of C. It's simply the group of yeah, so it's very explicit in this case. So we can simply see that this group, when you make the expansion, is a finite, of course, a finite dimensional group, and it's the group of automorphisms of the projective space. Okay, so in fact, it acts on the lines through the origin by permutating the lines through the origin as the usual action of PSL2. Okay, so in this case, this slice group, the one that we want to control by this procedure, is quite nice because it's in fact it's reductive. This is a reductive group. Yeah. Okay. Okay. So it's a reductive group. So it's in some sense, in this case, just by looking at the action on the slice, as I made before. Okay, so in this case, if this element here corresponds to a weight of 1, 1, 1, then the group which acts on the slice is the group of automorphisms of the projective space. So I can apply the classical the classical geometric invariant theory to understand this action here. Okay, so in fact, in particular, I can characterize when this bad situation here appears in algebraic terms by the vanishing locus of let's say some set of polynomials which are invariant with respect to this action. Okay. So in fact, in this case, I can apply the classical theory and to have this preparation of coordinates that prevents, as I said to you, the goal is to prevent this problem of full compensation due to the translations. Okay. But now consider the second case. So now I take lambda, the one parameter group, which gives weight omega y to the variable xi. Okay. So in this case, when you look at this slice group, you get the automorphism group of the weighted projective space. Okay, so the omega weighted projective space. So unfortunately, this group is not reductive in general. Okay, so except in general, well, except for the case where all the weights are equal to 1, and well, some in fact, for this group to be reductive, you should not have any sort of integral relation between the weights. Okay, so this is a problem because it means that we cannot apply the classical geometric invariant theory to the action when we try to understand the action on the slice. Okay, so for example, let's just give the very simple example. So we take the weights 1 and 2. I can describe explicitly which is the group of automorphisms of this weighted projective space. So it has a structure of a semi-direct product. So this is a copy of the 2 torus. And then there is a second part here, which is a copy of the additive group, C+. Okay. So this is the problematic part. The second one is the problematic part because this, when you have a piece of your group which of this form, then it cannot be reductive. So to be explicit, what's the action of this additive part? It acts on the, let's say, on a pair x and y, just by mapping y to the y plus c x squared. So this is an automorphism of the weighted projective space 1, 2, okay, which embeds a copy of the additive group inside. And in fact, this prevents this group from being reductive. And in some sense, this is a problem because this is what makes the theory a little bit problematic in higher dimensions, is that for the moment, we need some analog of this geometric invariant theory for non-reductive groups. Okay? Well, it's known that if such a theory cannot exist without any hypothesis, because there are examples due to Nagata where the ring of invariants is not even finally generated when G is not reductive. Okay, so in fact, there can be very, very bad, very, very wild actions of a group, even algebraically, when this group is not reductive. Well, so as I mentioned too, well, I not have time to do this, but in the case of surfaces, so when I look at the differential operator on surfaces, I can easily make a list of a complete list of possible slice groups which appear. So some of them will be reductive, and some of them will not be reductive, as the case that I mentioned. This is one of these examples that we have to deal with in dimension 2. Okay, but fortunately, each time that you have such an example, we can treat it by hand. Okay, because essentially, when the additive part is one-dimensional, there is a theorem which allows us to show that there can be no such bad phenomena here, as in the Nagata's example. Okay. So in this case, let's say in dimension 2, I can, in some sense, prove things by hand. So by the analogs of Kempf and Kira-Ness results. So there is this stratification, and we can make the machinery work to provide a resolution of singularities. And well, for what keeps me optimistic for higher dimensional situation is that there is, let's say, a lot of people working on this what they call the non-reductive geometric invariant theory. Okay, so essentially they are trying to define on which conditions we can make the machinery of, let's say, Hilbert-Mumford criteria and providing good quotients in the case of non-reductive groups. Okay. Well, so I'm observing let's say the progress in this area, but I think that at some point I will be able to use the results perhaps to generalize my strategy to higher dimensional situations. Okay. So I'm going to stop here. Thank you.
Thank you, Daniel.
I'm going to put the notes on the website. So there are more material than I was able to tell you. Yeah.
Thank you.
Extra time. Yeah. If you allow me more than 10 hours. Okay.
Est-ce que ce serait abusé de te demander dans tes notes de slide